Alrighty then. Oh, that was a satisfying clap. It actually maybe even made it onto the broadcast. Alrighty then. So since we're here now, hey guys, what's going on? Memes here. Yes, and now we are currently doing episode number 20, I believe. Who's counting? Of my monastery life. I'm gonna get up here for an hour and I'm gonna talk about some sciencey stuff and things, and uh, depending on what happens, this I have certain things to say. If there's somebody that I happen to know and they happen to have some time and they want to pop up and they want to share some thoughts, then maybe we can do that. I am fully curating that. I'm sorry. I used to do the more extreme. It's like, oh, yes, oh, we can have anybody on. And then you realize there are certain people that just kind of throw the groove off and everything. So I went from kind of more of the free speech extremist. It's like, okay, now, are you doing this because it's very valuable to you, or are you just doing this to be a dick? And I say that as a dick. It's my middle name. Not like I like literally. My middle name is Dick. But I digress. Okay, so we're gonna lay out as we let folks come on in from the YouTubes, the Twitters, the X's, whatever the heck you want to call it, from all the corners of the internet. We can conjugate, we can have words, we can figure out what might actually be going on. And Rick, I okay, I can't say I would never do such a thing because that would be a total lie. But if there are certain things you would like to share with the class, you are more than welcome to. I know you're very busy though. New scientist, new scientist. I'm just saying Archimedes law of gravity. I think that is right up their alley. I'd happily actually write them a short draft of the email. I just need to know which version you're using and stuff because I feel like that is right up their alley. I'd meant to email you that, but okay. But for today's topic, let me start. Okay, I did take a picture. Hold on, wait. No, Thad may have wrote more things down. Those little nuggets of where you just need to check. It's like, wait a second. As long as it was on the board within the past couple of weeks, we can just go back to it. Okay. Let me. No, not that one. This one. Yes. Zoom away. Okay. Just in case. I wouldn't want knowledge to be lost. That might break some certain rules. Okay, put this back in. But today we're going to be talking about the Dark Energy Spectroscopic Instrument Survey, aka DESI, and some of the very interesting findings that they seem to have found. And again, there might be a bias because I think it's in South Africa, so it has a southern hemisphere bias, but we'll find that though at least the current results tend to hold, there seems to be perhaps an unexpected, or depending on which model you happen to be a fan of, perhaps expected gravitational activity from more of the southern hemisphere of our ecliptic, or whatever they want to call it. AKA, you got the general direction we think we're going, and then from whence we came. And it seems the generally way that we're going is a little bit less activity than from whence we came. It also maybe there has something to do with the so-called axis of evil with the cosmic microwave background. Now, again, I must admit, I am very biased. That's one of the reasons why we're going over the results right now, just because if I'm going to take some of the words that come out of my mouth seriously, and I was going to say, well, what might things we would expect from certain of these surveys, I would tend to assume that there would be more activity from whence we came, or at least it would be a wee bit hotter. And those particular reasons, well, I'm going to speculate. We will conjecture ahead. Don't worry. That is as part of the subtext that we have in there. Because again, maybe there are some folks out there that have all the answers to life, the universe, and everything. Maybe it's 42 or not that far off, but I don't know. But it is fun to speculate, and even if you got folks that have different ideas, different ideas gel together, and you might have a person that they were almost there, they almost figured out something fascinating, but they were just held up, and then it just takes a random offhand comment, and all of a sudden it's like, oh my God, duh. And that person goes on to do great things. Now, these people may have already done great things, but one of the things you learn from history and just even my personal life experience is that you'll have like big names that are credited with all these things, but you don't always have the et al. The et al is all the other people that went in to help make that possible. So that brings in a number of questions about I don't know. I feel like there were some old words that spoke of beware of idolatry or something. It's I don't know. Maybe there's some wisdom in that. But I'm not here to preach about random stuff like that. We're here to talk about the Dark Energy Spectroscopic Survey. Or technically, it's an instrument, but it's the instrument doing the survey. So, did I? Okay, I cleared out all the tabs over there. Let's see. Ooh, ooh, that's very exciting. All right. Yeah, no, that's a math thing. I mean, no, there's a lot of math. It's also a lot of very interesting math that comes up. It makes one question. Hey, why might water be there? But all right, let's I think it's this guy. I need tabs on after. All right, let me close out that one where I'm sharing myself here. All right, so here's where we're gonna go. We're gonna go over to our window over here. Don't even know. Oh no, I broke something. Oh no, my God, they all broke. Hold on, let me. Oh, these are all PDFs. Okay, hold on. Let me. Axis of Evil. Ah, okay, fine. Click my PDF thingy again. There we go. All right, so that's part of Meerkat Pulsar timing array. They're part of this, and this is from the monthly notices of the Royal Astronomical Society starting the beginning of this year. They made all their articles free access. There ain't no more paywall. I'm gonna thank Professor Keating for that because it got brought up to him, and he's like, "Listen, hey, no, this stuff is paywalled." And I don't know. Now again, I got nothing wrong with people making money and surviving and stuff, but isn't it the Royal Astronomical Letters? Isn't that funded by the royal family? Is kind of the give back to being very blessed in life or something? I don't know. Okay, so we're gonna scroll through. I think this is yeah, this goes through a lot of the data. Don't worry, I haven't gone through all this, but as you can see, got a lot of data laid out there. I think it's this guy. Yeah. So we're just going to get to these pictures. Okay, so this is the picture that we use. What the heck are we looking at? Okay, so this is quantifying a radiometer map and cleanup anisotropy frequency p value. Okay, long story short is the areas that are kind of more reddish yellow, or excuse me, yellowish over here, there seems to be some more activity. And over here, yeah, the bluish purplish stuff, okay, there seems to be less activity. Okay. So as you go through, they're looking at it in different states. Okay, this is at 7 nanohertz, this is at 14 nanohertz, this is at 21 nanohertz. Okay, they detect a pattern, and they're also varying it by 7, which I'm sure there's no reason they're doing that, but I've complete conjecture on my part for a coincidence. But as you can see, it does tend to be a little bit more kind of activity if we're going to take this as our equator over here. The long story short, based upon a whole lot of smart people, it appears that our direction in the cosmos is going this way. We're going this way, and down here is from whence we came. So there does seem to be some more activity going on down there. And I think the sigma, I think it's like 2.6 or 3 sigma. So again, it's pretty good. Okay, so was it results are consistent with okay, I was wrong. Isotropy, okay, of greater than 2.3 sigma level range. Okay. So their confidence in the results That's a little under 2.5 sigma. Okay, so that ain't bad, but again, it's hey, you can have flukes, you can have a 6 sigma, and maybe it was totally cast out. This is one of the more recent papers. I think this was from December. Excuse me, November 13th of this year. So let's Meerkat timing array. Is this Meerkat timing array? Let's just see. Okay, Meerkat pulsar timing array. Okay, so the 4.5 year data release, noise and stochastic signals. Okay, so long story short is what are these things here? What they're doing is they're using what's known as a pulsar timing array. So what's a pulsar? A pulsar is essentially it's an astronomical object that perhaps it's a black hole, perhaps it's a neutron star, whatever it is, it's a massive thing. It's rotating ridiculously fast. And basically, you see like those like jets coming off of the pulsar. So you kind of, I got a board, so I might as well use the board. All right. Then you get some astronomical body over here. You got, all right. So we got a black hole, a star, whatever it is. This thing is rotating ridiculously fast, like probably pushing like the Eddington limit, or no, is that for total mass consumption? It doesn't matter. Basically, this thing is moving ridiculously fast, and then you'll get usually like a gas cloud or something around it, we think. And as this thing is spinning around, you have infalling matter. But as it's getting compressed and everything, it's got less angular momentum. So eventually, you're going to get basically it shooting off like these jets from its poles. Okay. And these things, they're since they're spinning these jets and everything, they kind of have a wobble to them. And they have a very particular wobble because if you stare at them long enough for years and years and years, you're basically going to figure out the general wobble. Okay, this jet will end up pointing towards us and our detectors every, I don't know, 0.7 nanoseconds or something like that, where basically as there's a little bit of a wobble, so we got a little bit of a wobble. So eventually the jet, this is the same thing, will be pointing towards us at some point. So we got Earth over here. We got our little lens for our detector and everything over here. And there's some person that's operating. This is not the scale. This is not the scale. But eventually we're going to get the detection so we can figure out, okay, what's going on. All right. This is a particular frequency, unless something were to act upon it. And that's the whole point of the pulsar timing array. The pulsar timing array is like, all right, I think for the study, they usually like 63 or 69 pulsars. So basically, what do they have? They got all these different pulsar here, pulsar here, pulsar here, pulsar here, there, pulsar here, pulsar everywhere, a pulsar. Okay, not everywhere, but at least in enough places where we have this enormous amount of potential signals that we can map. And again, most of these do happen in the southern hemisphere because, well, it's a southern hemisphere observatory. So, but essentially, you'll have all these things. All these things will have different jets. And if you study them long enough, you'll notice that, all right, well, these are going to twist at a certain frequency. And then we can get those frequencies down. And then what happens is if there is a very large gravitational effect, let's just say you had, it's conjectured primarily this phenomenon of our vibrating universe and gravitationally, according to our instruments. Let's just say you had a couple of supermassive black holes, and a couple of these really big guys. This is the conjectured reason why I'm not saying that this isn't why. It totally does make some sense. But if these guys are kind of going around each other and then they infall, it's going to create a lot of gravitational waves. So you're going to have this wave going through space time, whatever that is in and of itself. And as this wave goes through, you're going to see a slight deviation from our high precision measurements. So basically, if you're measuring a lot of these guys for years and years, you can get down their frequency, because there was at one point before we see it, I think it was about 10 to the minus 12 seconds or something, like 10 trillionths of a second. something like that. A million billion trillion. Okay. At one point, they were considering using the pulsar timing arrays to replace atomic clocks. And then we built better atomic clocks, so we didn't need to actually do that. But we apparently, according to our observations, know these very well, or at least the timing of them, what they should be. Now, if you were to have a very large, to observers like a cataclysmic gravitational event, like two supermassive black holes going in, falling, and merging, it's going to release a lot of gravitational energy through the medium. It's totally not the ether. We can say space time, we can say superfluid like material, but no ether. Why? It's a trigger word. But we have these gravitational effects, and they're going through. All of a sudden, these pulsars, which should be according to our measurements, have very specific rates in which we're going to have our observations. They're going to deviate just a little bit. Okay. So what am I talking about? So you may have heard of what's known as LIGO, the laser interferometer gravitational observatory. LIGO. I'm sorry. I know those words, but I actually haven't said them out loud in that way. And what the heck is LIGO? Okay, so LIGO is basically this facility in, where is it? Right now, I think it's like New Jersey, Princeton, or something like that, wherever that is, where it's like, okay, you get your building, you get a building, you get a building. Okay. And you got about 1 kilometer apart. 1 km, 1 km. I believe this is how the experiment is set up. And then basically, you're shooting a laser to here, you're shooting a laser to here, and these lasers should cancel out. And you got to do all this accounting for all this statistical noise, trucks going by and turn sneezing, all that jazz. You got to figure all that stuff out. And yeah, we also have a couple. I think we got one. I think there's one in India, and there's a third one, I think, in the Northwest somewhere up around these parts. Maybe Washington State. I don't recall. But essentially, what happens? These laser beams coming from like a kilometer apart, they should be able to cancel each other out, because if they're going at the same frequency, that light should cancel. Assuming they're perfectly lined up. Now, there was to be a gravitational wave waving through at the particular frequency. There's going to be a little deviation, and then we should be able to extract some data from that. Well, what might be going on? We also might want to point our telescopes in a way, because there may be an accompanying supernova or something like that we can actually observe. We get another one of our big lenses, our telescopes, and then we get a little person down here, very happy because they observed something. Yay! Okay. But this only works for higher frequencies, the frequencies of the mass range of, maybe if it's a couple of neutron stars. Basically, I think the gravitational things, I think the total product that we believe we have measured is about 30 to 60 solar masses in total of whatever ends up coming out there. So basically, smaller, but still ginormously massive to, I don't know, beings like us that are maybe, I don't know, a few dozen, few hundred kilograms or something. When you're talking about something multiple masses of the sun, pretty massive. But this frequency is much higher than the frequency of something so freaking ginormous. It's going to have an array of pulsars actually throw their timing off. Technically, you just wave your arms, and that's a little bit of a gravitational wave. But for us to actually detect that from billions of light years away, yeah, probably not so great. But you got a couple of things that have like the mass of the Milky Way or something like that in it, and they infall and they cause some form of cosmic kablooey or something like that. Yes, it's gonna have like a very, very low tone. It's just, you got that bass. We got that bass. Maybe not the bass we're looking for, aka very low frequency. We have low frequency, low frequency. Okay, it's going to throw this timing array off, and that's the whole point of these papers. Because what they've done is they have their sample, that they've been observing now for at least like 4.5 years or so now. And basically, they're detecting certain amount of activity, as we saw from our thumbnail. And we'll go back to it right now. What do we got? Oh, we got some more friends here. Oh, we got David. Good to see you, David. Oh, Morbius, Krell. But, hey, hey, hey. No, no, no. It looks like Morbius. All I know is I really don't know. And I just expose myself to a lot of really smart people. And it's kind of like if you're going to learn a foreign language, well, if it's physics, if it's math, you should expose yourself to that language. Even if you don't understand, you'll start to pick up things. And maybe you get to the point where maybe you could have a bit of a conversation. And then you reach the next barrier, which is you start to need to do calculations. Now, we're very blessed to live in a day and age where we got tools like Wolfram Alpha, so you just literally put in the question, and even if you're not don't know all the math symbols, you use like the Wolfram GTP or even some of the newer Chat GPTs. I think the one with Canvas and stuff, where it's like, could you write me some Wolfram language code and just ask the question there? Now we even have agents. Personally, I would recommend going through and learning it as best you can. So all else fails, if you had a calculator, or God forbid, maybe you were in a period of time where you only had a pencil and a piece of paper and just time to think and do hand calculations. But we're very blessed that we have tools that do like a lot of the heavy lifting for us. But yes, David. Old MacDonald had a pulsar, E-I-E-I-O, something like that. Sorry, terrible, terrible joke. Yes, yes, it could be. Hopefully, we don't have any gravitational tsunami warnings, because by the time we figured there's a gravitational tsunami coming, um, I think it would already be here. Something, something traversing medium at the speed of light. Uh, It's a limit. At least it seems that way. Um, that's a very interesting question. Uh, I don't know. I mean, maybe using it as a form of clocks, but then again, at that point, we would probably have. We already do have better atomic clocks. Um, I can't comment intelligently on that. It's. I feel like that's been asked before. It's. Oh, that we do not talk about the New Jersey drones. I'm sure they're not just policing the turnpike like good little boys, and not drones that were captured by other nations and reverse engineered our tech or anything. 'Cause that's never happened. See, that's why I talk about science. If you get me on those things, I will make everybody angry. This is why I don't get invited places. Because it's like, all right, yes, we're happy, we're saying things that make sense. And then you just have a glaring error. And you try to keep your mouth shut, but people keep on making the same error. And then you point it out. And then there is much screaming and yelling, and people get very butthurt. I apologize. Nobody would ever get butthurt on the internet. Yes, it is Washington, where LIGO is. Oh, oh, that's a cool thing. I don't know. Did they do visitor days? I know Perimeter occasionally has different things set up, but yeah. Okay, yeah. No, I stand corrected. You're right. There is one in Louisiana, Louisiana, New Jersey, and I think there is one over in India or something. Uh, oh, they do have Discovery Center and Clash. See, that's why I like those places. It's like, okay, I'm not gonna lie. I am a fan of the Museum of Science, Boston. Why? Because I went there when I was a young kid, and they have a ginormous T Rex. I have no idea how actually accurate it was. It's kind of had like the dark tannish, maybe like a little bit of a hue, but kind of like a greenish little bit, but mostly brownish skin. And you can go up to the second story and see the T Rex, and they have the Omni theaters. See, that's the cool science stuff I think we need more of, and hopefully technology will be able to leverage that at some point. Okay. So after my bloviating there, let's go back over here. Let's take a look at some of these pretty pictures. Okay. So this is the 25 page. Okay. So let me just see. Okay. So these are millisecond pulsars. Okay. So let's just read the abstract and give credit to oh god, Miles et al. See, there's a lot of people contributing to this. And I'm also afraid because those are a lot of names, a lot of those names, I'm terrible at names. Okay, well, we will read their abstract. I should remember to add the links in the doobly-doo below. Also, timing arrays are ensembles of regularly observed millisecond pulsars, timed to high precision. Each pulsar in an array can be affected by a suite of noise processes, most of which are astrophysically motivated. Analyzing them carefully can be used to understand these physical processes. However, the primary purpose of these experiments is to detect signals that are common to all pulses, in particular, signals associated with a stochastic gravitational wave background. To detect these, it is paramount to appropriately characterize other signals that may otherwise impact array sensitivity or cause a spurious detection. Okay, so this is their second data release. Okay, so they had a total of 83 millisecond pulsars over 4.5 years. Cool. All right, let's go back to our pretty picture one. Oh, yeah. All right. Oh, this one. Yep, that's what we were reading. Okay. So I got some math in there. Oh, we got our friend 12. Da, da. Okay. Give me those. Oh, no, it was in the other one. This is the data. Oh, why do I have two? Oh, this is the three. And this is Grunthal and all. Okay, this is the accompanying one. This is the one that has the pretty pictures. Okay. So we'll go over this real quick. And an accompanying publication, the Meerkat Pulsar Timing Array, MPTA. God. Anybody that's been in any corporate environment, you're going to realize the list of acronyms for different things literally goes on forever. I remember working for a Fortune 100 company once. It's literally, they give you a thing, I don't know, and it's 10, 15, 20 pages. And it's just basically just acronyms, the things, the department, blah, blah, blah. It's like, all right. I think even, I think one of the, even like the higher up, it was just like, yeah, nobody actually reads that. Just know that things are available and just look it up. I might just be making that up, but okay. Collaboration reports tentative evidence for the presence of a stochastic gravitational wave background. Okay, now what they're talking about that is essentially there seems to be waves waving everywhere. Okay, so there seems to be gravitational activity, at least according to their original timing. I think about a magnitude or so larger from all directions than what they were expecting because they have a specific frequency range. Um, the three most sensitive frequency bins were the 7 nanohertz to 21 nanohertz, so the 7, 14, and 21 nanohertz. So different ones they're trying to combine with additional data to try to clean it up and try to figure out what's going on. They found a noteworthy hotspot in the 7 nanohertz cleanup map with a p factor. Okay, so that's basically that's the error, I believe. It's been a while since I've done statistics of you messing with the data because it's a term called p hacking. Whereas if you play with and you massage the data enough, you massage it enough, it's kind of like a cat on an electric blanket. It will just turn to like butter and just kind of fall into almost whatever position you need. Uh, But okay, so it looks like there's a small p-value, so we're assuming that most of the data may actually have just come from the actual error in our instruments. At least that's how I'm taking that. Any statisticians, uh, please correct me. Okay, so using spherical harmonics. Oh, that's always good when we see those friends mentioned. Okay, we're doing the summation of the summation, all the stuff over there. All right. Ba-ba-ba. Again, 12 pies. I think we could always use some more pi. Here we go. Okay, so this is the 7 nanohertz thing. Okay. So notable hotspots. Okay, it does seem to be okay. It does seem to be very quite hot over there. That's okay. I'm looking at this in a little bit more detail here. So I think this is where they had their timing arrays and stuff. And again, it has a southern bias. because it's a southern observatory. So, okay. So then as we go through here, okay, that does seem to be still more hotter over there, but we got activity going on over here as well. And then over here, it's like, okay, it does seem to be a bit more dispersed as well, but okay, it is more south of the ecliptic, but again, it's a southern ecliptic survey. So I mean that necessarily shouldn't be that interesting. But okay. So we've got a couple more ones here. Now that is different than this one. Because this is saying, okay, this is 7 nanohertz. They're saying this is clean. So I believe what they're talking about there is they're removing um, the other potential effects. And then when you have it with the other effects, such as SNN are shown in the clean map column. P-values, encouraging small p-values for minimum SNN typically indicate a problem in the data analysis pipeline. Okay, so the actual data rather than their interpretation. So cool. All right, so the maximum SNN values. Okay. Okay, 7 hertz maximum. Okay, so somewhat unusual of p of 0.03. Okay. And point of detection source. Okay, the clean maps. Destin there's isotropic background. Okay. So, all right. So the interesting thing. Okay, yes, our current angular resolution of about 23 degrees. Yes, they only have so much range, and again, it's the right tool for the right job. So if it's being able to show this, then we can be like, all right, where are our blind spots? Can we get a better angular resolution? Can we do we need to survey at different frequencies? Maybe, I don't know. Could we use something like Planck for a gravitational wave background? Apparently, oh, I think that's what LIGO is. No, LISA, the the laser interferometer space observatory. Apparently, that's coming sometime in 2030. We hope. Uh, so, oh, what are they doing for LISA? So, all right, we had LIGO over here. So it's basically LIGO. All right. LIGO. Like Lego, except we got I. Why? Because it's an interferometer. Why? That's a fancy science tool we use to measure stuff. Okay. But okay, we're doing this, and this is typically smaller-ish. So small black holes. BH. So small black holes. But what if we want to do this for the ginormous ones? Well, my friends, to everybody's shock, we basically just do something like this. A box. Let's add some solar sails on so we can tell it's a satellite. A satellite or a TIE fighter, whatever. They do the same thing over here. Yeah. Then we have another friend over here. Yes, my friends. It literally looks to be the exact same thing. Laser beam there, laser beam there, laser beam there. All right. So we're essentially doing the same thing, except instead of like 1 kilometer apart, I think we're doing like 100,000 kilometers apart. Uh, okay, this would be root 2, so that should be like I'm just filling in here. It's about 100,000 kilometers. We'll do about one. Uh, 141, I think, is about root 2 kilometers. Okay, we're just doing another triangle. That's all it is. It's a triangle rather than like, all right, we got our building here, we got our building here, we got our building here. It's like, all right, we get our satellite here, we got our satellite there, we get a satellite there, and then we measure the differences. Why? Because we need to have it on a much larger magnitude. And if you're out in space, you don't have to worry about the dump truck going by. There's a space dump truck going by. That might even be more interesting. Mr. Musk, we're paying attention to you. I digress, though. Okay. As we're halfway through the show, I should probably actually get to a point. Oh, welcome, K Show. Yes. Oh. Oh, David is, yeah, yeah, waving, yes. Waving our hands generates waves. It's almost like swimming or being in a pool or the ocean or nature. We might be able to learn something. I know. Rick is saying that Lisa should be able to detect gravitational waves all the way back to the Big Bang. That would be fantastic. Um, that's why it's so exciting and everything. It's like, okay, so I'm gonna go on a slight bit of a history rant, and again, I'm sure some of this rant is going to be a little bit off or anything, but the general statements I believe are probably true, or at least also fall within the standard spectrum of humanity and responses to different stuff. So, okay. So back when I was kind of like growing up and stuff like that, we would occasionally see pictures from like the Hubble Space Telescope because the Hubble Space Telescope went up in was it late '80s, early '90s, uh, something like that, and it went up there, and then we start to calibrate and take pictures, and they seem to be kind of fuzzy. Why? There was an imperfection in the lens. Luckily, it was in low Earth orbit, so we were able to send the repair crew up with a new lens, replace the lens, and then when it turned on, and then basically after that embarrassment, it's like, oh, okay, one of the chief scientists was like, "Here's what we're gonna do. We need to make up for this public embarrassment. What are we gonna do? We're gonna stare off into nothing." That seems like such a crazy idea. Why don't you take a couple of pictures of the planets? Be like, oh, look, pretty planet stuff. He was like, no, 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 no. We're gonna do something crazy. Maybe it wouldn't work out for him, but ultimately, that's how we got the Hubble Deep Field, I believe. Was it? We stared at a particular patch of sky that appeared empty to our standard instruments of the time, but the Hubble being about a 3.5 meter telescope and then not having to deal with Earth's atmosphere, could stare right at that deep patch of sky. We got the deep field, and oh my God, people started losing their minds. Okay. For a number of reasons. Number one, it's like, oh my God, we're literally looking into the heavens. We're literally looking back like billions of years. We're literally taking a picture of the past. To our knowledge, it takes a while for stuff to get here. Okay. Now, what also happened is a lot of our previous beliefs about what might be going on seem to get challenged. Before, people like, all right, well, if there's a big bang, well, obviously, if there's some expansion or observed expansion, whatever it might be, it's like, it's obviously going to be slowing down. 1998, 1999 roll around, and all of a sudden it's like, wait a second, things appear to be getting faster. WTF, mate? What's going on? Yeah, and I think there was I think Professor Krauss was part of that crowd or something, and I don't know, some people won some prizes and stuff. But that was an unexpected thing. But certain tools like our experiments, our observations, our telescopes, like the Hubble, like James Webb, like the Planck satellite, like Lisa, should hopefully be and stuff. We're getting new data. We're able to refine our models. And as we refine our models and we get better data and everything, occasionally the models that we use that seem to work pretty well for a while, like, yeah, the planets are obviously going around in circles. I mean, certainly. Until it's like, okay, we got some more data. Yeah, circles don't kind of all funky and stuff like that. Okay, maybe you're a fan of the Tycho model. Hey, I ain't telling you what to do, but I personally seems like I think we've put some stuff up in space, but just personal opinion there. Uh Basically, as we get new data and stuff, certain models, it's like, okay, how about running a circle? What if we used an ellipse? An ellipse? What are you talking about? That's too complicated. A circle, you just get a point, you get a string, and you draw it around so you're equally distant. Bada boom, bada bing, never a miscommunication, except for our standard error. Now, you might think that's more difficult, but and I can flip and ellipse, it actually just has two foci. So you can literally do the exact same thing You choose your two foci, you get a string, you get your marker, you go around, you're going to have an ellipse. Who knew? Apparently, some people did. But what I'm saying is, as we get more data, and as we become more certain and we learn more about stuff, even just on our own planet Earth here, um, is it really that surprising that some models that served us well for a while, is it, maybe we just need an upgrade? That's all. I mean, can you keep the same Chrysler minivan for 20 something years if you have like an unlimited warranty? Sure. Does that always mean to a certain point that you should? I don't know. I have to ask Echelon. I'm sorry. I'm sorry. Much love to Echelon. Oh man, miss you, buddy. Miss you, buddy. Hope to see you come back at some point. But it's very interesting that okay, we're getting these new models. Excuse me. We're getting this new data. And with the James Webb, which was the whole point of that whole Hubble story, is basically we got new information that challenged what we believed. And I'm pretty sure if we go back, you're going to see a lot of the same thing. Cosmology uprooted, astronomers baffled, scientists have no idea why. Because we're getting new data, we're digesting it, and then okay, maybe we were just wrong about some things. Maybe our old models are right, or maybe we're coming up with better models that can explain more with less. What do I mean with that? Now, ultimately, you need to follow the evidence. My dad was an attorney. He always told me, he's like, Memes, you follow the evidence. Now, you got to follow the evidence and you got to lay out your case. So, if we're using our standard concordance model, I'm like, all right, so we had like okay, we start off with some hand wave. We have some cosmic fluctuations there. Okay, so there's some wizardry going on that we don't understand. Fine. Okay, you start off, and then we had the entire universe in an infinitesimally small spot, and then all of a sudden, cosmic kablooey, big bang, bada boom. And then we believe it expanded between 26 to 78 orders of magnitude, depending on which podcast you listen to and which studies you're citing and everything there. Okay, and then we got to our current portion where we believe there's some reheating going on. What's that mean? That's all of a sudden matter starts to take place. What do we even start having protons and neutrons? Start having atoms, as we know, and everything is about 3,000 degrees Kelvin is believed by a lot of folks. And then we're just in our current state. We're just expanding. Okay, how do we get to something that's accelerating? Oh no, we're getting further away from all the matter. It's going to keep on spreading out. It's going to be a giant rip, and the fabric of space time itself will just vanish, and we'll just all be poof. Sounds like the plot of a Ren and Stimpy episode. Don't push the history eraser button. What'll it do? Maybe something good, maybe something bad, but we'll never. You can tempt a neurotic cat. What's wrong with you, Ren? Okay. Pop side and 90s kid analogies aside, what's the whole point? The whole point is Hubble, we started getting more information. We started being able to better digest what actually might be going on. Did we really be surprised with James Webb? Oh, it comes about like 30 years later. It's like, yes, it did. Is it any less surprising? Doesn't seem that way. Maybe it's more surprising. Maybe it's just current present bias and stuff like that. Because I just grew up with seeing a lot of those things, and now it's like, oh my god, we're looking back. We're going to like redshift of 17. So like 200 million years into our current model of the observed universe, and there always seem to be a bunch of galaxies with a bunch of young stars and stuff, and they're chilling. Doesn't seem to be a whole lot of gas and stuff around. Why might that be? But oh, here's what we need to do. Long story short, I think we're getting more information. We're going to be able to update our models. We're going to be able to better think. Well, that's very true. I used to think Mars had canals, and obviously there are people chilling there and the sun. And I think a lot of people thought those things within the past 100 years or so. So Oh yeah. Well, a lot of people still saying space time is a traffic brick. So where are we? Okay. So, but there was also something that helped inspire this, and shout out to Professor Keating, the Chancellor's Distinguished Professor of Physics over at UC San Diego. But yeah, I'm going to reshare this so I can get some audio. Let's see. He did a quick short, which okay, which I'm sure, since this is for academic and learning potential, he's totally fine with me sharing because he's a good professor.
It turns out that gravitational waves have a beautiful propensity to turn the polarization of the microwave background in a very particular orientation. And we can, by mapping the orientation of the microwave background and its polarization, we can divine the existence or lack thereof of waves of gravity called gravitational radiation. And if detected, that doesn't prove a theory that we can get into called inflation, which is the most popular cosmogenesis model that we have, but it gives very, very, very strong circumstantial evidence for it. It turns out.
Okay. So I found that very interesting. Number one, he's right in that as you get evidence for it, doesn't necessarily prove that this is the thing. No, you got a bunch more evidence. And if it was part of a prediction, then you're going to give it more credence. And you'll be like, okay, maybe this makes more sense. Now, as he says, it could be evidence for inflation, whatever that may or may not be. It may also be evidence for other things as well. Hey, upcycle. Good to see you. Good to see you. It's very interesting because as you go through these different communities and different folks in broadcast, you see different folks in the chat, and it's very fun when you see people you remember. And usually try to say hi or something like that. It's amazing what a few nice words can actually do. It's like maybe you don't always have to be a dick, even though I am. That's a fact. But okay, number one, I love his intro. Why? Let's listen.
The gravitational waves have a beautiful propensity to turn the polarization of the microwave background in a very particular.
I like the peas. I just watched Mr. Popper's Penguins again for the first time in years. So is it like Patty Pettiwinkle or something like that? She uses all the peas inside. I'm looking at the kids' book, so it was fun there. But also, he's talking about the gravitational waves, and if there happens to be a particular layout, kind of we were looking at, and that kind of reminded me a little bit of where are we? Let's go to our standard. Which one? Oh, I closed that. Oh no, I need a stop share. CMB axis of evil. Why? Because we like using very hyperbolic language. Maybe that's telling us something. Hey, XYZ. Good to see you, my friend. We're getting to the point after most of the broadcast, but what else is new? Let's see. Okay, so let's look at some interesting pictures. Okay, so here's an interesting picture. This is brought to us by our friends at New Scientist, who I totally stole this picture from. So as you can see, there are some. Okay, did it go to it? Is it not sharing? Oh, hold on, I did the wrong thing. I need to share the window. I apologize. Here we go. All right, from New Scientist. Okay, so again, they're saying that the CMB is basically evidence of cosmic inflation. Why? Well, if it's going to inflate that fast, it's going to be little bits of imperfection here, little bits, and those will be emphasized. So we would expect to see some hot spots and some cool spots. Okay. Well, the interesting thing is, as you can see over here, does seem to be hot, does seem to be cold. It does seem to be a very notable cold spot over there. But there also does seem to be some heat going on. So I'm just like, all right, now look at this. Look at this. And I'm like, all right, maybe I just need to squint harder, but I'm like, hold on. So I'm like, uh, It's like going to the eye doctor. Better, worse. Better, worse. Better, worse. Okay. Um, I'm showing the picture here again. These are very minor fluctuations, and like I don't know, it's probably like the fifth or sixth significant digits, about 2.730 Kelvin, uh, maybe 2.725, something like that. All right, well, let's actually just go to the axis of evil article. Okay, so why am I saying this? Okay, so all right. So the cosmic microwave background radiation signature to the large scale to next. Okay, here we go. The motion of the solar system and the orientation of the plane of the ecliptic are aligned with features of the microwave sky, which appear to be caused by a structure at the edge of the observable universe. Specifically, with respect to the ecliptic plane, the top half of the CMB is slightly cooler than the bottom half. Furthermore, the quadrupole and octupole axes are only a few degrees apart. These axes are aligned with the top and bottom divides. So you're going to find other images just for the sake of searching for stuff. Hold on. Axes of evil. Okay. So you're going to see things like this. So we got Dr. Becky. She's covered this as well. And all right. So you see something like this. It's like, wait a second. Hot, cold, and then hold on, there's a better one, I think. Shows uh, it's basically like hot, cold, hot, warmer, cooler, warmer, cooler. Okay. Well, you know what this means? This means I gotta reach out again to Professor Keating and actually interview him so I can actually learn more about this stuff because it's fascinating. Uh, but all right. The long story short, the whole point of what it's got to exist. It's got to exist, or at least as far as I can observe. All right. So the whole point of this, and again, why I'm biased on this is all right. So apparently, let's do a little erasing. All right. Beautiful as my pulsar timing array. I quickly drew on the board. I would uh, I would much more recommend seeking out professionals that have actually used these instruments, that have actually spent the past half decade of their lives figuring out what's going on. Because I have not used that instrument. I gotta have enough trouble using a microwave. Last thing you want to do is give me control of a microwave satellite. Uh, pun intended. Okay. So what we're talking about is all right. So if we got observable universe, okay, got an observable universe. All right. So let's say we're going this way. Throw a little Earth here. It's happy little Earth. Okay. Earth and our observable universe seem to be going in this direction. So we got our little plane, our ecliptic plane over here. Blah 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 blah. Consider this our horizon. Okay, we got our horizon over here. We're going this way. Okay. So up here seems to be cooler. Down here seems to be hotter. Okay, so if in the direction we're going is a bit cooler, it's a bit hotter here. I mean, that just sounds like normal thermodynamics. It's like, oh, hot, and so it's going to end up going to a cooler region and stuff. Okay, I can understand that. It's like, all right, it's you put some hot water in some coffee or water. Uh, okay, cool water, hot water. You pour the hot water in, and it's going to end up dispersing, and it's going to end up just heating it up. But that hot water is going to disperse. Okay, why? It has more energy. It's you just have molecules just hopping around. It's of course it's probably going to go a little higher, assuming gravitational effects. Um, But what's interesting is that's according to the CMB. So we go up. That's the cosmic microwave background. It's the CMB. This is what we see. And again, there's minute differences and stuff, but we're looking for clues. We're trying to figure out what's going on. And then if over here we have north, if there is, and again, this is a southern biased observatory, so we gotta acknowledge that, but I'm assuming they've accounted for many things, but we have to put that in there. If there's less activity or gravitationally observed phenomenon via the pulsar timing away, those 83 pulses they've been studying for 4.5 years. And if the southern from whence we came, there's more activity. And this is the DESI, the Dark Energy Spectroscopic Instrument, but we're talking about its actual results in the survey. Okay. So, would it be an unreasonable thing if we were to conjecture, since based upon our more recent observations that we're going to need to continue to do, that if according to our CMB map, where we're going is a little bit cooler, from whence we came is a little bit hotter, and according to the DESI 4.5 year results, if it appears, based upon the survey, that where we're going has less activity, and from whence we came has more activity, is it the most unreasonable thing to say that, I don't know, let's say if our observable universe is about, it's about 10 to the 26 meters. Okay. So if we got a radius of about 10 to the 26 meters, something like that, it's of the magnitude of the observable universe. Okay. Hypothetically, if the realm in which we live and we persist in was a heck of a lot more ginormous than that, is it unreasonable to, let's say, if there was a point of origin, call it origin from for our perspective of beings like us. Let's just say there was, I don't know, some cosmic hyperpump. Let's assume that it was persisting. We'll just use a lemniscate symbol to represent it, aka an infinity symbol or a sideways 8. So let's just say if there was some cosmic, we'll call it a hyperpump. Shout out to Kali, the first one I've heard use that term. We had some cosmic hyperpump that perhaps was ingesting whatever might be there, compacting it down so it's in a really hot, dense state. And then let's say you have some oscillation, kind of like perhaps we were being sung into existence, if you would, might be the poetic term for it, because well, if mass is simply just a frequency in a particular term and yada yada yada. I know there was a lot of yadas right there. I'm taking the large level thing, but basically, if we have frequency, we got wavelength and everything, depending on how you want to slice it. That would seem to make a lot of sense. So it's kind of if something was coming out here, let's just say hypothetically you had a whole bunch of stuff going in here. Maybe it was almost like you toss a stone into a pond. It's going to be some ripples, some activity. Or if you had a hot dense, let's say the mass of the observable universe is about 10 to the 52 kilograms. Okay. So if you got a ginormous amount of mass, so hypothetically, if we were to enclose, let me use a different color. If our actual, so to speak, universe was a ginormously amount more ginormous than our observable here, it's almost kind of like I think we did the thing with the little blender and stuff, and uh, you got a little vortex motion going on. Yeah, a couple of drops of little food coloring or something. It's kind of like it reminds me of the crystal lighting stuff. I always used to get those energy drink things, but before I realized they were very acidic. And I'll just take a thing of water and I just splurch some in, and then I'm like, seems to be dispersing in a very particular way. Now, where it came, it tended to be a bit denser and everything, but it seemed to very quickly diffuse. I'm like, is it possible like that? Something like that might be going on? Now, again, I'm very biased because we were just talking about this yesterday as we were conjecturing if you had some form of an eternal cyclic cosmology, or call it a Big Bang, steady state, whatever you want. But essentially, if you had a whole bunch of mass, let's say about 10 to the 52 kilograms, just for argument's sake, it got compressed, and this thing is going around, and it gets all spewed out. We're going to have a very hot, dense, call it plasma, quark, gluons, this, that, the other thing. Might it just start expanding and everything taking, I don't know, it's not like a sphere is like the minimal or maximal form. Was it circle is maximum for one, sphere no, sphere is, I always forget that. I know the cube is unit one, but if it's going to spread out, and well, if we came from here and it was hot, wouldn't that mean it's going to be a bit hotter around here? And thing that's been out and had time to kind of disperse and stuff, and is coming from a hotter region, isn't it going to be a little bit cooler up here? And if you had some ridiculously violent cosmic kablooey or something, probably going to be more activity around here. And until you run into another, I don't, I don't like the term bubble universe or anything like that, even though that kind of sounds like what they're talking about. But unless you run into anything else up here, it's probably going to be a little less activity. And again, it's only about 2.3 sigma or so for these initial DESI results. And of course, we're going to want to map more of the sky with more precision and everything. But I don't know. Is it that unreasonable a thing to think that we could account for some results? I mean, yeah, we're conjecturing some toroidal, small knot that's literally cinching the field configuration of reality together. Yes, we are conjecturing that. A hypersphere, external realm of thermodynamics. I mean, I think other people have already conjectured that, and some folks say, maybe that makes sense. Maybe it does, maybe it doesn't. But if we can set those as potential axioms or potential reasons, and again, we follow the evidence, doesn't this kind of account for dark energy? And again, if we are observing this, I'm not going to throw Einstein under the bus or anything like that. It's like, at least we need to follow the evidence. Um, might that explain that if maybe universe as a whole is older than 14 billion years? I know, such a stunning and brave claim right there. But if it was a lot older, to observers like us, yeah, it might look about 13.7 billion years. Okay. Um, overall, if it's been around for longer, that means there's a lot more time for different stars to be doing their star thing, shining light, massive amounts of neutrinos going around. If you had some cosmological process that literally just recycles most of the stuff there, we would have a lot more time for a lot more cosmological and astronomical processes, such as star formation, planet formation. Basically, there might be a lot more cool dark matter out there, and it also doesn't hurt if you have a physical mechanism to explain why dark energy is its thing, because at this point, dark energy seems to just become a thermodynamic recycling process. And depending on where you are, oh, maybe we're kind of accelerating, maybe we're slowing down. But if you have a point as a source, things go all the way around, and it's back at a sink. I I don't know. Is that why rho vac is equal to minus p vac? It's, again, I'm not a cosmologist. I'm a dude on the internet following some evidence that's had a chance to actually speak with some really smart folks. those of whom that might be watching now temporally in the future. Oh, Dan. Let's see, Dan. You got chat. Yes, the power of yada yada yada. Just make sure you source the yadas. Uh, uh, No, no, yeah. I think the videos will help a lot more, Jax. That's the thing. I can say these things, and if you've been following and you've seen a lava lamp and a snow globe, okay, maybe it kind of makes sense there. But you got to put those things together and everything. And we're just trying to do it. I mean, Thad just kind of laid out a model. I'm like, all right, let's look at the model. Let's listen to a whole bunch of smart people. Let's look at some information. And again, it might just be a little bit of evidence. But if that little bit of evidence becomes a little bit more, then you start to build a pile of evidence there, and then you just try to go the path of least resistance, kind of like what? But there's a lot of stuff going on. Oh, look at me. I've already exceeded my time slot. But yeah, so that's what we got for today. So we're just trying to figure out what might be going on, just looking at some measurements. And again, we'll follow the evidence wherever it goes. And again, this might just all be bunk. If it's not bunk, it might explain a lot. And I'm pretty sure any explanation that can help you figure out about 70% of what's going on, that ain't a bad start. But that's all we got for today. Take care of yourselves, everyone. It's a crazy world out there, but it's open for a better tomorrow. Peace out.